Back everyone. So today's lecture is on matrix and its connection with linear transformation. So in the last lecture I explained linear transformation, and in this lecture I will walk you through what are matrices and how they are connected with linear transformation. So if you haven't watched my previous videos, then I do recommend watching them as they are very important to understand this lecture. All right. So before moving forward, I will just give you some refresher on linear transformation because that is very important. So linear transformation. So as I told earlier, that linear transformation do two things to a vector. LT do two things to a vector. And linear transformation is applied on what? Linear transformation is applied on vector or the entire space. So either it is applied on one vector, or like maybe applied on the entire vector space. Let us suppose R2. Okay. So it do two things. So the first one is it scales a vector. So for example, this is the vector, right? So you apply the linear transformation. Let us suppose T. Then it will scale the vector. It will either just scale the vector, and if it scales the vector, then this vector will remain in this straight line only, right? Either it will be stretched, I mean its length will be increased, or it will be squashed, its length will be decreased, or it may be flipped and then stretched, whatever happen, but always this vector will remain in this line. So the span of this vector is this line itself. So this is one thing, which is scaling of vector. And in scaling it covers everything, stretching, squashing, flipping the vector, everything. Okay. The second thing it can do to a vector, like depends on the linear transformation, is it can simply rotate the vector. So you apply this linear transformation, so maybe it doesn't scale the vector, but it rotate the vector, do some rotation, right? So the first thing it do is scaling of vector, the second thing it can do is rotation of vector. So maybe it just rotate it by 90 degree, right, or any angle, but yeah, rotation of vector. So this is the second thing. And the third thing it can do is a mixture of both. That is, it can both scale and rotate the vector. So maybe this is your original vector, and then you apply this linear transformation. This is a third linear transformation. It rotated the vector and also scaled it. So maybe it rotated the vector by 90 degree and also scaled it by 2 times. So both scaling plus rotation of vector. So only these things are done. Only two things, either scaling, rotation, or a combination of both. So this is what linear transformation do. And why it is linear? Why it is linear? That is also important, because transformation means transforming the space plus changing it, right? Like function. But we are interested in linear transformation. So why it is linear? Because it preserves certain properties. Because it preserves certain properties of the input vector space, right? What are those property? I just mentioned three, very simple, like easy to remember. Lines remains lines, lines remains lines after the linear transformation. Second is equally spaced remain equally spaced. So basically whatever, for example, we have two lines in the input vector space, after transformation the two lines remain equally spaced. So equally spaced remains equally spaced. And this is not just about line, it's about any figure, any 2D figure. In the last lecture we saw that a square before the transformation, I mean the points on that square remain equally spaced, right? So equally spaced remain equally spaced. And see, it doesn't mean that before the transformation you have a square, and it I am saying that after the transformation it also remains a square. No, that is completely wrong to say. That square may become a rhombus if you do a shear linear transformation, shear transformation. It can become a rhombus, or it can become any shape, right? But the thing is, if we take any 2 points before the linear transformation, the space between those two points, I mean those two pair of points remains equal. So uh, uh, for example, these are 3 points in the linear transform sorry, in the input vector space. For example, the space between this point and these 2 point and these 2 point is equal, let us suppose. So after the linear transformation also, the space between these two pairs of point remains equal. Okay, or you can say that the grid lines of the xy plane remains equally spaced. And the third and most important is origin remains origin. Origin remains origin. That is, zero vector doesn't change. Zero vector doesn't change. Or we can also say that t of 0 is still 0. So only these three condition, because of these three preservation, these three properties are preserved. That's why it's an input. That's why it's a linear transformation. If any of these properties violated, then it is no more a linear transformation. That is very important to remember. All right. So I think this is the refresher I need to give in the starting few minutes. Now I will take you to the today's lecture, like matrices, how they are connected to metrics and all. Okay, so we need to understand that what is the connection between linear transformation and matrix or matrix transformation. Because it is also a transformation, right? That you will know just now. So let us suppose we have a vector x, right, in the input vector space, and we know that any vector x is nothing but a linear combination of its basis vector, right? So x is nothing but a linear combination of its basis vector. So x1, let us suppose e1 is the first basis vector, x2, e2 is the second basis vector, and so on, so forth. Okay, so here x belong to Rn. So if x belong to R2, then it is in xy plane. Okay, if x belong to R3, then it is in the xyz space. So for generality, I just take x belonging to Rn, and could be anything. Okay, so because I have shown in the previous lecture that x is nothing but a linear combination of basis vector, right? So any vector x belonging to Rn is just a linear combination of all the basis vectors ei of Rn, right? So this is very clear to you. Like if you have seen my previous lecture, then it's very much clear to you. I went into detail. Okay, now let us suppose I apply a linear transformation t. I apply a linear transformation t on x, right? So I need to see that what this linear transformation t do to x, right? So applying a linear transformation t to x, that basically means this one, right? And like in the previous lecture, I have mentioned, like I have explained you the one of the property of linear transformation, like why it is called linear. Like this thing, these three properties are graphical representation or visual, in visual terms, but we are talking about maths here. So how we represent linear thing, that I already explained, right? So with using that property, this becomes first of all, this becomes this, we can split it into additions, right? Right. So which property I am using here? I am using here this property. Linear transformation of addition of two vector is nothing but addition of the individual linear transformation, right? And these properties I explained in detail in previous lecture. Now I use the another property of linear transformation, the second property. In that I can take out this scalar outside, and this becomes this xn en, right? And which property I am using here? I am using this property, a times v is nothing but a times tv. These are the two properties I am using, right? So now this can be written something like this. uh, what is this x1 xn? These are the components of the vector x, because x belong to Rn, right? So for example, let us suppose if x belong to R3, then what is x? It has three values, a b c, for three x's, right? So this is nothing but x1, this is x2, and this is x3, right? So this addition, I can write it as this. I can first place all these transformed values, t1, then e2, so on ten, and then I can simply write the vector x. This is nothing but matrix vector multiplication, right? So if you want to simplify it, I can write it for now like this: x1 up to xn, right? So this thing is nothing but the matrix consisting of the new basis of this transformed what do you say, space, right? And this is nothing but the r x vector, right? So if I see uh, what is this, for example, uh, every vector, as I already told you, that every vector x is nothing but a linear combination of its basis vector, right? And now what is this, te here? This is nothing but what t do to the first basis vector even, how t transform the first basis vector, how t transform the second basis vector, and so on and so forth. And this combined compact representation is nothing but the matrix A. So matrix A is nothing but it's a matrix consisting of new bases as columns, right? So e1, e2 up to en were original bases, right? These were original bases. Then we applied t, then we apply the linear transformation t, and now the new basis is te1, te2 up to ten. Okay. Also, like here I should not write this, it's my mistake. So it's not a vector, it's a component, right? It's a component of vector e, so it's not this. Okay, I just removed all these. These are not vectors. These are not vectors. All right. So These are the original bases. Then we apply the transformation T, so this becomes the new transformed basis, right? And matrix A is nothing but the collection of these transformed bases as columns. I will give you an example to make things more clear. But also one thing which is very clear from here, uh, this thing, because this thing is AX, right? So this tells us that linear combination is indeed a matrix vector multiplication, right? Because this is matrix, A is matrix and this is vector, so this AX, what is it? It is matrix vector multiplication, and this AX is equal to this thing, right? And this is the linear combination. So linear combination is indeed a matrix vector multiplication. All right, so I think it's clear to you. Now what is the conclusion here? I started from T but I ended at A, right? I started applying T on the vector X but I ended having A as a A as a I ended having A and X as a product, which is matrix vector multiplication. So the conclusion is all linear transformations are just matrix transformations. That's all. So either you write this or either you write in the compact form. There is no difference. So linear transformation and matrix transformation are the exact same thing. So linear transformation, LT, and matrix or matrix transformation are exactly same. What is the difference then? If they are exactly same, then what is the difference? There is a key difference. Now I will tell you what is the key difference. The difference is linear transformation is an algebraic way. I mean, it's an algebraic way of representing thing, right? Whereas matrix is a geometric representation, geometric or visual representation. This is algebraic representation. That's all. That is the difference. And because it is compact, obviously, like instead of writing this entire linear combination equation, I can simply write A into X. So it's also a compact representation, right? Now let's do a exercise for even more clarity, so that you get much better clarity. Do we have any better color? I would say this one. All right. So let us suppose we need to find matrix of a linear transformation. Let us suppose we need to find matrix of a linear transformation. And what is that linear transformation? Let us say that linear transformation is rotation. Okay, so we have already I already stated that this is the basic thing, that transformation of X is nothing but transformation of these basis vectors, I mean, and then product of X. So this is nothing but A times X. This matrix A is nothing but the column of the matrix A are the transformed basis vectors. So I can also write that columns of A are transformed basis vectors. That is why basis vector is a very important topic, because if you know everything about basis vector, like how they are transformed, then you know everything. So for example, let us suppose we have a linear transformation uh, rotation, let's say by theta, right? And I already explained why rotation is a linear transformation. If you are not like sure why it is, then go and watch my previous lecture. I will share the link in the description. All right. Okay, so we have these two basis vectors, right? This is simple R2 space, right? We have the first basis vector E1, and we have the second basis vector E2. All right. Now let us suppose we rotate this. Let us suppose this is a circle, and we rotate this basis vector. We rotate the entire this linear transformation L. By the way, is doing a rotation of theta anti-clockwise. So let us suppose we rotated this entire uh, xy plane by theta. So this after rotation, this becomes t of E1, right? So this is theta degree, and this become t of E2, right? So let me erase this. All right. So this was E2, by the way, right? And this will become t of E2 after rotation. I rotated. Okay, and what is the angle of rotation? Angle of rotation is theta. This is becoming little clumsy right now. Sorry for that. I should have made it bigger. Anyways, so this is basic trigonometry here, right? What is the value of t of E1? This is nothing but cos theta E1 and sin theta E1, right? Because see, this is the thing here. This is theta, and this we already know, this is E1. So the x component is this, which is cos theta E1, and this is the y component, this is sin theta E1, right? So this is t of E1, and similarly we can calculate t of E2. T of E2 will be minus sin theta E2 and cos theta E2, right? And with using this equation, I already stated that t of x is nothing but x1, because it's R2. So x1 t of E1 plus x2 t of E2, right? So I can write it as this. Wait, just give me a minute. Just give me a minute. My eraser. This is yeah. So even x1 cos theta, x1 sin theta E2 minus x2 sin theta, x2 cos theta, and then we can combine, and we will get the matrix representation as cos theta sin theta, this column, minus sin theta cos theta. right? And apart from this, here it will be okay, sorry, I did a mistake, I did this mistake, sorry. It is even here, x1 here, right? मैंने उल्टा लिख दिया. x1 was outside, x2, this was e1, this is e2, this is e2, right? Okay, but you will say, okay, where this e1 and e2 went, x1 x2 are here, sine theta e1 e2, because like usually in r2 the standard basis is nothing but 1 comma 0 and 0 comma 1, right? So if you place e1 is nothing but 1, e2 is nothing but 1. So if you place 1 1 1 1, so this matrix become this. Otherwise you can write e1 here, e1 here, e2 here, e2 here, but I mean in r2, because I have given you example of r2, in r2 this e1 and e2 is nothing but 1, so there is no point of writing, but you can write that, okay? And if you are taking any basis where if you are taking a different basis where e1 e2 is not 1, then you have to write e1 here, right? Anyways, so what is this? This is nothing but rotation matrix, and we know that matrix and transformation is the same thing, so we can also call it rotation transformation. All right, I think this is clear to you. So we get the matrix of the linear transformation. So what was the linear transformation? Rotation by theta degree anti-clockwise AC, and we get the matrix for that, and this is the matrix for that. So the matrix A for this linear transformation T is cos theta sin theta minus sin theta cos theta. And what are the columns? I already told you what are the columns. Columns are nothing but where E1 landed after transformation, right? And this is where E2 landed after transformation. And in this case, in this example, E1 is nothing but I hat and E2 is nothing but J hat. So you can simply say that, okay, the matrix, the columns of matrix is nothing. The first column is where I hat landed and the second column is where J hat landed. And if it is 3D, if this transformation is in 3D, then the first column is where I hat landed, the second is where J hat landed, the third is where K hat landed. Okay, so I think that clears a lot of what you say, confusion between the connection of matrices and linear transformation. So like if it is still not clear, like I will give you an example, like this same rotation example. Okay, so let us suppose the same thing, we have this xy plane and we rotate this xy plane, linear transformation, let us suppose this is 90-degree AC rotation, 90-degree AC rotation, right? So where will be I hat and J hat landing after this? So this is I hat, that is 1 0, and sorry, this is J hat, that is 0 1. You did a 90-degree rotation, so if you do 90-degree rotation, then this I hat will land here where J hat is right now, that is 0 1, and this J hat will land here, that is minus 1 0. So this is nothing but transformed I hat and this is nothing but transformed J hat, right? So as I already told you that the matrix representation of T, the transformation T, is nothing but where the first basis vector land, where the first basis vector I had landed, it landed at 0 1. where the second basis vector j had landed, it landed at minus 1 0, right? This is where I had landed, this is where j had landed, and we can also say this is nothing but t of I hat, transformed I hat, and this is nothing but transform j hat, right? And if you go here, like the generalized representation, we has this general matrix A equal to cos theta, sin theta, minus sin theta, cos theta, rotation by theta degree. But if I rotate it by 90 degree, so this become cos 90 0, sin 90 1, minus, this is minus sin 90 minus 1, cos 90 0. See, we get the same, we get the same thing, right? So whatever I solved here, it's a generic thing, but I have given you visual interpretation of that, right? So before the transformation, I had was at 1 0 and j at 0 1. You do a 90 degree anti-clockwise rotation, you landed here. Now someone asks you that what is the matrix representation of this linear transformation? Very simple. The first column is where I had landed, the second column is where j had landed. That's all. That's all you have to do. And why this is important? Why this matrix representation is important to us? Because if now I give you any random vector, let us suppose I give you this vector, let us suppose, which is v. All right, let's draw it somewhere else. Let us suppose I give you this vector. I give you this vector v, and now I ask where it landed. So first of all, you don't need to make any calculation at all. You know it's a 90 degree rotation, so it will land here. Oh, sorry. It will simply land here, right? T of v. So v is nothing but minus 1 0, and this is what? This is nothing but 0 comma minus 1. But because this is very simple, but if I give you any random vector like somewhere here, I mean some vector something like this, let us suppose this, you will get an idea. Okay, this will go somewhere here, right? But you need to know the exact value, and that's why these matrices will come into picture. So using the matrix, you can transform any vector, because the matrix is nothing but linear transformation itself. Like it's a compact representation of linear transformation. So you can use matrix A to transform any vector. So let us suppose I have I need to know where a vector v goes, right? So all I need to do is just do a matrix vector multiplication. So this is nothing, this is my matrix representation of the linear transformation. V is nothing but its component are Vx and Vy, right? And I can write it as this 0 1. I mean this is how we do matrix multiplication, right? And this we also call that as that V is nothing but a linear combination of columns of matrix A, right? This is nothing but V, because this is linear combination. I already told you what is a linear combination. Go watch my previous videos. So it's simple addition and vector addition and scalar multiplication, right? This is scalar multiplication. This is also scalar multiplication, and scalar multiplication will give us this vector again. I mean this will give us a vector, and then we are doing vector addition. So this is nothing but 0 v times x. Scalar multiplication is giving us a vector again, minus vy and 0. Now after scalar multiplication, this is vector addition, right, which is nothing but minus vy and vx, right? So now if you want to know what is this v was initially minus 1 0, and now after transformation I know that any vector vx vy will be transformed to minus vy and vx. So what was vy was 0, so minus 0 is again 0, and what was vx is minus 1. So I think that is correct, right? minus 1 comma 0 is transformed to 0 comma minus 1. So this is right. So see, that's why matrix is very important. It will be tedious and difficult you to know where this vector landed after applying the linear transformation using the traditional way, I mean this linear combination way, this one, right? But it is very easy for you to do with the matrix multiplication, and in fact matrix multiplication is indeed linear combination, right? This is linear combination, LC. So you see, this is very connected. I mean, I won't even say connected, it's the same thing, matrix and this linear transformation, right? So I think it is clear to you now. Now if it is clear to you now, we know that matrix transformation and linear transformation are interchangeable, right? So matrix transformation and linear transformation are interchangeable. So the same properties of linear transformation applies to matrix transformation as well. That is this one. If you see, right? So what is this? This is basically the matrix M, and you are multiplying it with scaled version of vector X. So what you can do, you can simply first multiply matrix M with the vector just like this, just like we do here, and then you can scale it. And the second property is of linearity is this. Right? So this is like matrix, you are multiplying it with the addition of two vectors, or what you can do, you first multiply by individual vector and you add the result, right? So now if I go to transformation, or rather linear transformation, that is important, right? So this was the matrix representation of linear transformation L or T, which is A. Then you multiply it with a vector X and you will get some vector as an output. Usually it is represented as B vector. So let us suppose you get an vector as an output B, because matrix vector multiplication always give you vector, right? So let us suppose X lives in Rn space. So let us suppose R2xy, right? And let us suppose A is also n cross n. Then V will belong to Rn only. So it's same as saying if X is in the xy plane, that is X belong to R2, and after the linear transformation V also belong to R2, then your this linear transformation or the matrix representation of that is nothing but n cross n or Rn cross Rn. Just write it as n cross n, because Rn cross Rn means something different. Okay, right? So we can, in compact form, this is the crux, this is the what do you say, summary of this entire lecture, what I am doing right now, that T is, in this particular case, T is a linear transformation from Rn to Rn. By the way, it could be from Rn to Rm. This n need not to be same. You can have a linear transformation from R2 to R3, from R3 to R2 as well. But that we will come in the upcoming lecture, because it has its own understanding. It has its own visual understanding, right? So T is a linear transformation from Rn to Rn. Then its matrix representation. Is A, which is n cross n. All right, am I making sense? I think I'm making sense, right? So if I conclude this lecture, then I can say that column J in matrix for T comes from applying the transformation T to the input basis vector. That is the first point. If I conclude this lecture, conclusion, right? This is the first point is columns J in matrix for linear transformation T comes from applying T, that is the linear transformation, to the input basis vector E, right? So metrics are not just bunch of numbers. If till now you are thinking, we have studied in 11th or 12th in maybe undergrad, if you think that metrics are just bunch of numbers, it is just used for solving linear system of equations, then you are wrong. It's not just a bunch of number, but they are representing the linear transformation. They are the transformation of space. So matrices are nothing but transformation of space. And because they represent linear transformation, so matrices linearly transform only, because they are the representation of linear transformation only, right? So matrices linearly transforms space or a given vector. So whatever you have studied about linear transformation in the previous lecture, the entire thing mapped to matrix, because matrix are itself linear transformation. It's just the representation of the linear transformation itself, right? So I think that's all for today. Let me see if anything is remaining. Linear transformation, visual meaning. Yeah, I think that's all. Most of the things are covered. Matrix and its connection to linear transformation. So just for an end note, I can mention that linear transformation and matrices are equivalent, right? I mean, linear transformation also transform the space linearly. It has the same property. Matrices also transform the space linearly. It has those same linearity property, right? So it's the representation, compact representation of LT, and this is algebraic, right? This is algebraic and this is geometric, means visually. That's all the difference. Okay, so that's all. So make sure that all these concepts are very much clear to you, because for GATE foundation is very important, because you know that even after GATE, giving GATE exam, in many IITs you need to give a written test, and in some IITs you need to have interview as well. So these foundations are very very important, otherwise like it will be very difficult for you to clear GATE exam. All right, so that's why I'm giving a lot of time. All of my videos are going above 40 minutes, because I want to explain it pretty well. Okay, so in the next lecture I will just have a short video on follow up on matrices, their properties, multiplication of matrices, and also what are non-square matrices, what they do, and I will introduce one or two minor topics which are very important for solving questions, because next to next video onwards I will be solving a lot of questions. 2-3 consecutive videos will be on questions, previous year linear algebra questions. So make sure you clear your concept fundas very well. Okay, and yeah, at the last, if you like my videos, then please subscribe my channel, like my videos, share with your friends, your colleague, with any ML engineer, with any GATE aspirant as much as possible. Like, I will be very happy. So okay, thank you, see you then, bye.